problem, which is our kind of nucleation and growth type problems. So let's go ahead and launch right into it. So I'm really interested in looking at the crystallization process of polymer A versus polymer C. So we know that both A and C are semicrystalline, or actually we know that actually A and C are both semicrystalline. So we know that polymer A looked like this, so C. And then we had our other polymer, which is all these kind of bulky groups and these bonds like this, and we can kind of look it back up. And H amide linkages, H bonding, etc., etc., etc. So we know that Tg of C is greater than Tg of A. And thus, we also know that Tm is approximately equal to 0.5 to 0.8 Tg. So it says fill out the crystallization rate as a function of temperature for both polymers. Be sure to label curves and explain when does nucleation dominate, when does growth dominate. So I'm going to say that my A is going to be red, and I'm going to put my C as my blue. So C. So now always remember temperature here, not undercooling. So I know that for my polymer C, if I was to draw a plot like this of I versus delta T, I know that my C would take less undercooling than my polymer A. I need more undercooling. So essentially what this is saying is that I need, basically, so if this is temperature, if I need large undercooling, I need A to be at very low temperatures in order to crystallize, whereas for my blue, I could go just like this. So again, it's useful to kind of work in between these plots, but always check what is this value here. So, and we also know, for example, for blue, at high temperatures, what's dominating here? Diffusion or growth. What's dominating here? Nucleation. So low temperatures, nucleation dominates. Again, it's just kind of the flip, the reverse here. Here, at high undercooling, that means my nucleation dominating, low temperature. Remember, delta T is equal to Tm minus T at the temperature of my system. This is going to be my nucleation and growth value. So you know how to work back and forth essentially between those problems. Excellent. So let's see. How does the equilibrium lamellar thickness scale with the degree of undercooling? Again, the degree of undercooling in your system, not necessarily this kind of critical undercooling. Well, we know from our expressions and from our notes that L is going to be, actually switch to red here. L is going to be proportional to 1 over delta T. So as I increase my amount of undercooling, my delta T, this kind of critical lamellar thickness, L star, will start to decrease. Why? Again, I don't need to kind of maximize as much. As my temperature lowers, I don't need to kind of maximize my enthalpic interactions by increasing my favorable enthalpic interactions here. So if temperature is lower, this term, which pushes towards basically disordered and not crystalline material, will decrease even more, so I don't need as thick of a lamella. So that's where that comes from here. Let's see. How does melting temperature vary as a function of lamellar thickness? Well, we know if I have long lamella, I have a larger number of intermolecular interactions. And if they're closer together, that increases my strength as well. So as L increases, my Tm increases as well. And again, this brings us to kind of a very handy table that we had in our notes. Let's see if I could find it somewhat quickly. I'm getting close to it. Here it is, this handy table. So you can kind of see here as what is going to happen to my melting point. Again, as some of these kind of parameters here, you can kind of see these relationships. And actually, we're going to go through one of those and then a problem in just a second. So let's go back to our exam. But we know that one pretty straightforward. And then finally, what is the driving force for crystallization? What energetic term opposes crystallization? Well, here we know that entropy opposes crystallization, these favorable enthalpic terms as well, but we could also kind of write it in terms of nucleation is minus delta GV volume, creating volume, but surfaces are energetically unfavorable. Excellent. So be ready again. There's going to be probably quite a few problems on this. So, and finally, tell me whether the following will increase or decrease Tg and Tm respectively. Will any of these factors affect lamella thickness? So let's go ahead and think about that for a second here. So let's go to these parameters. So let's first focus on what's going to happen to Tg, Tm, then let's figure out any that are going to affect L. So if I increase the number of branches, So if I increase the number of branches, my free volume essentially, will increase, and that is going to make my TG become lower and lower and lower. More free volume available, I'm going to have to cool down even further in order to kind of freeze that polymer in place. So my TG is going to decrease, and the number of branches, let's go ahead and draw this. Yeah, undo that. Can I undo a line? Oh yeah, there we go. Let me draw here just very delicately. So I'm going to decrease my TG, my TM. If I increase my number of branches, that's going to decrease. And lamellar thickness, let's go back to that in a second. If I decrease my molecular weight, again, same thing. I'm adding free volume, increasing my amount of free volume, decreasing TG, and you can kind of imagine it asks you what's going to happen to free volume possibly as well. So here, increasing number of branches, free volume increases. Decrease molecular weight, free volume increases. My TG thus must decrease. And then here as well. Add very, very long and bulky but extremely flexible side chains. So long, and bulky and flexible. So even though it's long, even though it's very flexible, again, it's still long and bulky. It's going to be hard to kind of rotate. So that is going to increase my TG. If they're very long and bulky, it doesn't say rigid. They're still flexible. So that's going to be very, very hard to crystallize. So that is going to decrease my TM. Rigid bonds in the backbone structure, increase my TG, increase my TM. Polar or charge groups in the backbone or side chain, again, increase. What about kind of my critical lamellar thickness? If I have polar groups, that should decrease that critical lamellar thickness. Again, it wants to, kind of form that crystalline region. This should decrease as well. Again, that critical lamellar thickness. So you can kind of see the difference in this. Let's go back to our kind of chain here. The kind of critical lamellar thickness, again, that's going to still depend on kind of your kinetic parameters, but you can kind of estimate, that critical lamellar size. So what about very long, bulky, but again, flexible side chains? Again, that's going to be a little bit of a fuzzy issue. It's going to be kind of fairly difficult to, it's going to increase. Again, very flexible. I'm going to have to increase that lamellar thickness in order to overcome that gain in entropic effects. Decrease molecular weight branches, that's a little bit of a trickier kind of issue to kind of go through your L star. But again, this is kind of more of a side project, but these are very, very interesting phenomena that you can kind of investigate and think about if we add this free volume component as well. All right, so that's about it. That is our exam 2. So good luck on the exam. Study well. If you have any questions, please let me know. And I hope this was helpful, and I'll see you all on Sunday for our review session at 8 a.m. sharp. All right, see you then. Thanks.